Let's talk about Taylor series and some subtle things that can happen with them. So if we start with a function like e to the x, we can build what's called its Taylor series by taking a bunch of derivatives, evaluating them at 0, and putting them into this formula here. For instance, if I just take the first two highlighted terms, I get the tangent line to e to the x. And as I add more terms, I get a tangent parabola, a tangent cubic, etc. And you can see that these equations are very closely converging to the function e to the x. I want to show a second example though, because for instance, if we start with the function 1 over 1 minus x, we can do the same thing and build a Taylor series, but it's not going to have the same behavior we just saw. You can see our tangent line and parabola and cubic are converging for part of the graph, but not all of it. There are parts of the graph to the left and the right where the orange thing never even. So why does this Taylor series equal 1 over 1 minus x? It doesn't. In fact, I've done some simplification up here, and you can kind of see that it's totally valid to plug in, say, the number 5 into this formula. You would get 1 over negative 4. But you can't plug 5 in here because this would diverge, it would go off to infinity. So what you can always do is if you start with a function that has lots of derivatives, you can always work them out and put them into this Taylor series, and that will always agree with your function at the point you picked. In this case, we're going to always work with 0. However, if you look for non-zero values, it might be the case that your Taylor series might not converge. That's what we just saw in the example. Plugging in 5 would not converge in that Taylor series that we wrote down. At this point, you might think, oh, well, if it does converge, then we're going to be good. It's going to equal our function, right? That's actually wrong. It's possible for the Taylor series to converge, but not to converge to the function we started with. In fact, here's the graph of a function and its Taylor series. The function is that black one on top, and the Taylor series is just the flat function 0. It's true that this function has derivative 0 for infinitely many times, and so when you work out the Taylor series, you just get a bunch of zeros. And so of course it converges, it's just always 0. But of course, this function up here that we started with was only 0 at one point. So even though the Taylor series converges, it does not agree with the function except at that single point. I do have good news though. In practice, your Taylor series will equal the function you started with a lot of the time. It works for any function that's called analytic, and these are pretty common. If you want to know the nuts and bolts of what's going on, there's a theorem called Taylor's theorem that says if you have some control of the derivatives, for instance, if they're all less than some fixed number m, then it's going to be the case that your Taylor series will converge to the function. There are some more details in there, but that's the basic gist. So for instance, the function sine of x has derivatives plus or minus sine, plus or minus cosine, and those are all going to take on values between -1 and 1. And so we could take that number m to be 1, and that shows no matter what x we pick, this Taylor series will be the same as sine of x. The same kind of idea works for e to the x. For instance, for any x between -50 and 50, well, any derivative is going to be e to the x, and so the biggest it could be would be e to the 50. So that shows if I plug in any number x between -50 and 50, this equation is going to be true. Now if I wanted it true for a bigger number x, I'd just start with a bigger number and I would have to modify this number m. So even though Taylor series aren't like a magical thing that always works, in practice they're a very useful tool.